transition from at least what I would call purely theoretical to now going into some of the applications. So far, all we dealt with were electrostatics, and that provided a nice framework for really developing a nice theoretical understanding of electricity and in the topic called electrostatics. What we're going to be talking about now is making our way into looking at electric circuits. And what we recently covered the parallel plate capacitors, and that is a electronic device that can that often do go into circuits. And so the parallel plate capacitor really provides us for a smooth transition from the theoretical aspect to the idea of electronic circuits. So, yeah, today we will be we also just finished covering the electric potential, that's the volts. And electronics often deal with volts, not with electric fields. And so now that we have covered the electric potential and got you familiar with what volts are, that also allows us to actually transition to talking about electric circuits. So this will be section 2A. Oh, where's my note section? No. Huh. Which I call circuits and electrodynamics. Circuits and electrodynamics. Let's first begin by defining a capacitor. You may be saying, wait, we already defined it. Unfortunately, we were looking at it in a very specific context, and what we care more about here is defining it in terms of its applicability. The last time we defined it, all we did was define it using its parts. However, let's talk about why capacitors are used in electronics in the first place. And that is, these are devices that can store electric charge. So these are devices that can store electric charge. So like a battery, you can store it for later use. Right? Batteries are simply things that store voltage, and then you can use it later. Capacitors can store charge, and can store charge for later use. Another thing that capacitors can do is to block surges of energy to protect circuits. It's kind of like when there's flooding, or let's say a city's about to be flooded, and the city townspeople are going to go in and just start, digging alternate paths or just digging large holes so that water can go in there. Do you guys know what I'm talking about? That's kind of what how the capacitor can act as a protection device, where charge, instead of overloading all the different parts of a circuit, it will just, majority of it will just go in and flood the capacitor, leaving all the other parts of the circuit unharmed. Now, I already gave this description, but I'll write it here again for completeness, for completion. These normally consist of two conducting objects that are separated and not touching. Now, so far, the scenario that we've been dealing with looks like this. We have two electrodes, and we hook up wires to them, and then we hook it up to a battery. Modern capacitors do not look like this whatsoever, because we need to keep them separated, meaning not touching. Because what would happen if the two electrodes touch? What would happen if they touch? Remember, in a capacitor, one becomes positively charged, the other one is negatively charged. What would happen if they touch? No, these wouldn't be like magnets.
Oh.
Yeah, what would happen?
Neutralize.
Yeah, it will neutralize. The electrons from here will go onto here, and essentially you're going to be discharging the electrodes. And then you're left with not a capacitor. And if you place nothing in between, then you need to be very, very careful so that they actually don't touch. Instead, what you can do is, I'm just going to be drawing a cross-sectional view. You can have an electrode here and the alternate electrode here. But instead of having nothing in between them, you put an insulating material in between. And this will act as a mechanical separation support so that you can push them as hard as you want together, but that layer of insulating material will ensure that those two electrodes will never become in electronic contact. So this would be an insulating material. However, even then, you still won't really find these because these are very space inefficient. And so one way that you might see them is kind of rolled up into a cylinder. Where the insulating material kind of be like right there. Now, in an electronic circuit, you're going to have many different electronic components, and it is not uncommon to have hundreds, sometimes even thousands of different components. To represented, would you want to draw any of these sketches over and over and over again? And hopefully the answer is no, because that'll take forever. So instead, onto what is called a circuit diagram. That's just a simplified version of the actual circuit. We can represent a capacitor by two parallel lines that are equal in length. Or, well, actually, let me see this. And please do not get this confused with the representation of a battery, where the battery, instead of even lines, has one line longer than the other. But these tend to be confusing, so people have come up with slightly alternate forms. So a capacitor also looks like this. You have one straight line and one slightly curved line. And the battery is also modified. Instead of two lines, you just have four, long, short, long, short. And on the battery, the long line is given, is in the direction of the positive charge. The negative, or the shorter line is for the negative electrode. So we're going to be using capacitors in a circuit, so let's begin by defining a circuit. It is a closed path. You have an electric circuit when you have a closed closed path of conducting material. Closed path of conducting material. So let's actually apply a capacitor into circuit form. So say if voltage is applied and whenever you see that, you simply understand that we're simply saying we hook up a battery to it. So battery applies a voltage. So if a battery is applied or a voltage is applied, then plates become charged. So in our circuit, let's say the diagram looks like this. So in our battery, the left side would be the positive electrode, the right side would be the negative electrode. In the capacitor, the left one would be positive Q, the right one would be negative Q. So here, one plate becomes positive Q, the other becomes negative Q. But one of the things that we discussed about a capacitor is that in between the plates you have an electric field. Last class, when we talked about the electric potential, we made a relationship between the electric field and the voltage. Meaning, in between the plates, there is some voltage across. There is voltage across the parallel plate capacitor. If you hook up a battery with voltage V, so with respect to this voltage, the battery voltage, what would you expect the voltage of the capacitor to be?
The same.
Yeah, the same is correct. To a first approximation. The voltage, and that's all you need to know. So for our scenario, yeah, it's the same. The voltage across the battery is across the capacitor. Meaning, once you hook up the battery, electrons are going to be transferred from one to the other up until you get some voltage, you get the same voltage across the capacitor as you do with the battery. Meaning, the charge Q has a relationship to the voltage that's actually across each capacitor. So here, charge, so it's voltage of battery is across the capacitor. So here, charge and voltage are related. So the battery is going to be transferring enough charge up until, boom, the voltages are the same, at which point the battery cannot make the charges go anymore. But what is that relationship? And that relationship is called the capacitor equation, or which I'll be calling the capacitor equation, which is simply Q times CV, where Q is the charge on capacitor, V is defined as the voltage across capacitor, and C is defined as the capacitance. Of the capacitor. This has units of coulombs over volts, which is also called a farad. F-A-R-A-D, which is short for named after Michael Faraday, who was one of the pioneers of this entire field. This C, or this idea of capacitance, is something that just characterizes the capacitor. Do you guys remember springs? Remember the spring was equal to, the force of a spring was equal to negative K delta X. You guys remember this? Where K was the spring constant. And that simply told you how strong the spring was. And that's related to things like the size of the spring, the material that the spring is made by, so on and so forth. And that's kind of what this idea of capacitance is. It's just showing you how good of a capacitor can this be. So, the capacitance depends on things like the size of the capacitor. So, are you using small electrodes or large electrodes? So, size of plates. Also, the distance in between the plates. As well as the conductivity of the material, so material properties. More importantly than saying what it is related to or dependent on is what C is not dependent on. C is independent of the charge and the voltage. So the capacitance has nothing to do with the charge nor the voltage. It's like the spring idea. Does the spring constant change just because you extended it a little bit? No, the spring is still the same spring, so it has that same spring constant. The external parameters does not change what the material is made of. So the capacitance is purely how the capacitor was made. What are the parameters of the construction? So let's do a few examples to make sure that one example so that we understand how to even read this equation. So let's say I gave you a capacitance profile. So what I'm plotting is Q versus V. And I give you three different capacitors. The first one has a profile that looks like that. Second one has a profile that looks like this. And the last one has a profile that looks like that. And the question that I really want to answer is, which capacitor has the largest capacitance? Which capacitor has the largest capacitance C? Let's see a show of hands. Who thinks it's capacitor A? Who thinks it's capacitor B? Who thinks it's capacitor C? It is capacitor A. And why is that? Well, let's look at our equation, the capacitor equation. Q is equal to CV. We have on our y-axis we plotted Q, so that would be our y. On our x-axis we plotted V, so it would look like the following equation of a line. Except for the Q is equal to CV, we would have plus 0. So you see everything's hitting the y-intercept is 0, which is what we would expect. And so if Q is y and V is x, then what is the capacitance in the graph?
The slope.
Yeah, what is M? M is the slope. And so A has the steepest slope, meaning A has the highest capacitance. So the answer is A because it is the steepest slope. Well, let's come back to this. So capacitance depends on the things like the size of the plates, the distance in between them, and so on and so forth. But it is not dependent on Q or V. So let's talk about how to more precisely determine the capacitance from its elementary variables. So determining capacitance. Now, in a experimental setting, so meaning in the lab, when you have a lot of equipment and tools at your disposal, so experimentally, measuring capacitance is extremely simple. All you need to do is measure the Q for a given voltage. Measure the Q for a given voltage, then you take the ratio, boom, you get the capacitance. However, this is a lecture, and so we don't really care about just purely experimentally, but we care more about analytical expressions because that gives you a more fundamental understanding of things. So let's talk about analytically. Analytically, can obtain expression for simple geometries. And we will be going over one such simple geometry, and that is called the parallel plate capacitor, which we've dealt with so many times before. So on our capacitor, we have positive charges, we have negative charges, and we have an electric field in between. And let's say we measured the plate area, and let's call that A. And we also place these electrodes at a specific distance, which we measured, and we will call that lowercase d. Now, if the square root of the area is much larger than the distance, or this is a fancy way of saying, if the plates are much larger than the distance in between them, then we have the infinite plate approximation, or essentially can assume a uniform electric field. Now from the section when we introduced the uniform electric field, we discussed the parallel plate capacitor, which had an electric field relationship of eta over epsilon naught, or Q over A epsilon naught. So this is from before. And on Monday, we talked about the electric potential, which was equal to E dotted distance technically it's the negative of that. And in a parallel plate capacitor, electrons would go from where to where if it's traversing the gap in between? Electrons would begin from where and end up where? Positive to negative?
Negative to positive.
This isn't energy, this is the electric field. No, electrons would begin here because that's where the negative charges are, and it would be attracted to the positive. Right, if we place an electron in the middle, it will go towards the positive. And so this would be our L vector. And let's recall what our dot product is. So when we get rid of the dot product, it would be cosine of theta, ED times cosine of theta. Oh, sorry, this is our distance vector, D. What is theta in this example, or in this case? 0? Incorrect.
Is it 90?
Not 90.
180.
Yeah, 180. Theta is the angle between the electric field and our distance vector. Electric field is this away, electrons moving which away? That away, and that's 180 degrees in between them. So if theta is equal to 180, what is cosine of theta then? It would be -1, meaning, in our case, V is equal to E times D. And we just discussed, we have the electric field in terms of its elementary parameters, the amount of charge as well as the area. So we can plug that in to our electric field, which would be Q over A epsilon naught times D, or simply QD over A epsilon naught. Now, however, this is not what we were looking for. What were we looking for? We were trying to determine capacitance. Capacitance. Where where Q is equal to CV, where when we isolate for C, it would be Q over V. But now we have the voltage in terms of its elementary properties, and so we can substitute our voltage in for that. And so we will get Q over QD over A epsilon naught. And what can cancel? The Q's can cancel. And then we're going to be left with, then the capacitance is equal to A epsilon naught over D. This is what the capacitance depends on. How large are the plates, and what is the distance between them, as well as this epsilon naught. So So the capacitance just purely is determined by how you constructed the electrode together, or how you assemble it. So let's do an example putting, utilizing this expression into use. First, we want to calculate the capacitance of a capacitor of 20 centimeters by 3.0 centimeters, separated by 1 millimeter of air. Second, we want to know what is the charge if 12-volt battery is connected across the plates. Three, what is the electric field strength? As well as 4, what area is required to reach 1 farad? What is the area required to reach 1 farad? So we have these 4 questions. What is the capacitance of a capacitor given by those dimensions? Let's begin with that one. We're asked for the capacitance, and we just derived a capacitance expression in terms of its elementary parameters, and that is A times epsilon naught over the distance d. Well, what is the area? It's 20 centimeters by 3 centimeters, so it's 20, let's use proper units. 0.2 meters times 0.03 meters times epsilon naught. I know that's 8.85, but let's just use this one. 9 times 10 to the negative 12 coulomb squared, Newton meter squared. Divided by the distance in between the plates, and that is 0.001 meters. And put in all those, and you're going to get 53 PF. What is PF? What is the F? Yeah, the F is farads. What is the P? It is a prefix for pico. You guys have to get accustomed to using prefixes, and it is in the handbook. This is the prefix for times 10 to the negative 12. So really, really small. So you get milli, micro, nano, then comes pico. But the prefixes are something that I expect everyone to be aware of. Two, what is the charge? What is Q if a 12-volt battery is connected? Well, Q, we see, comes up in our capacitor equation. Q is equal to CV. Do we know the capacitance? Yeah, we just calculated it, 53 picofarad. Do we know the voltage? Yeah, we're hooking up a 12-volt battery. So it's simply 53 picofarad times 12 volts, and you're going to get a value of 6.4 times 10 to the negative 10 coulombs. Third, we want to know the electric field strength. Well, we have our ED equation. V is equal to the electric field times the distance, meaning the electric field is equal to V over the distance, where the voltage is 12 volts divided by 0.001 meters, or this is going to be 1.2 times 10 to the 4th volts per meter. Lastly, what area is required to reach 1 farad? Well, we're looking for area given a farad. So we likely care about the capacitance as well as an area. And our capacitance equation has a capacitance and an area, so likely that's where we want to begin. So it has both parameters of interest. So that's that. But we're looking for area, so we can solve for area, which is equal to capacitance times the distance divided by the epsilon naught. What is the capacitance that we're looking for? Well, the problem specifying 1 farad. The distance between the plates that we use is 0.001 meters, and epsilon naught is 9 times 10 to the negative 12th coulomb squared Newton meter squared. And if you do that, you're going to get roughly 10 to the 8th square meters. Who knows how large this is? Is this the size of a school? Not school. Oh, what is it called? Is it a football field? Is it the size of a football field, a city, a state? What is it? Which one? Football field, city, or state? Who says football field? Closest to. City, closest to. Okay. State, closest. How large is Santa Clarita? Google it. You have it.
It's 183 kilometers square.
180, okay. I want meters squared, please. Although I could do that, but I'd rather you just give me the numbers.
183,000.
183,000?
That's not.
100.
I got 161 million in
Right.
meters squared.
Is it billions? Well, I don't really care about the numbers actually. We'll see.
So
How many, what is the power of 10?
You move it 3 times, so it's 183.
Okay, I'll just give you the answer. Okay, I'll just give you the answer. Santa Clarita is roughly 10 to the 8th meter squared. So if you want to get if you want to make a capacitor that is 1 farad, okay, take Santa Clarita, multiply by 2, stand both of them up straight, bring them up just so that it's 1 millimeter apart, and then you'll have 1 farad. So is that practical? Is that feasible? And you would say no. But here's the thing. With advanced technology and nanotechnology, more precisely, we can very easily get 1 farad by creatively tuning things on the microscopic scale. So what seems very impossible, or what was actually believed to be impossible way back in the past, is actually much doable because of things like nanotechnology. And so this is the reason why you want to continue learning, and this is why things are getting so expensive, because it requires a lot of high precise instruments, measurements, and people that studied a lot of time who charge a lot of money for their time, things like this. But ultimately, it does allow us to do things that were previously thought was impossible. So that's just a little bit of fact there. Let me give you also one alternate use of, it's technically not a capacitor, but this use of capacitance. So it's not just in terms of storing charge, but it's how your keyboards work. So let's go over how. So let's say this is, let's not look at the overall keyboard, let's just look at one button. And there's some sort of a spring mechanism that makes the button stand up, right? So when you press it, it doesn't stay down, it comes back up. But I'm not going to draw that spring mechanism, so just assume that there's a spring somewhere. But if we were to just look at one letter only, we can isolate some crucial features. In this bottom part here, what we have are two electrodes. So we would have one electrode here, as well as one electrode all the way at the bottom. And these, as long as these are electrodes, they have a certain capacitance. But what happens when you press the button? What happens to this distance? Oh, I forgot to mention, this is connected to the upper electrode. So the button is connected to the upper electrode. So when you press a button, what happens to the electrode? Meaning the distance between them goes down. We just discussed the capacitance is related to the distance. So what your keyboard does is it actually measures the change in capacitance. And when it changes by a sufficient amount, that's how your computer knows, oh, this button was pressed. The change in the capacitance is what is being measured. Also, your phones. How does your phone know where you touched the screen? How does your phone even know that you even touched the screen? Or how does your phone know to not register some random thing that touch your screen to know that it wasn't a finger? You guys know what I'm talking about? Are you guys following? It deals with capacitance. So your phone, let's say this is your screen, there's different sensors. Okay, I don't know exactly where the sensors are. I'm just trying to highlight the main idea. There's various sensors all throughout your phone. And let's say you tap right here. Your phone will know that you touched right here. Your phone will know that you touched right here because your finger has a certain capacitance value as well. And when you touch it, even though electronic signals are extremely quick, it's not instantaneous. Meaning, it's going to be communicating to this sensor and this sensor much faster than that one or that one. By knowing exactly how long it takes for each sensor to register that change in capacitance, it can back calculate, oh, it must have been pressed at this point only. Likewise, if you press here, which ones, let's number these, 1, 2, 3, and 4. If you pressed here, which sensor is going to be registered first? Right, 2, and then what? Right, and then 1, and then what? Then 4, and then 3. And this is how your touch screens actually work, and it knows where it actually touched. So this idea of capacitance isn't just for storing charge, but it is actually used to determine and detect, I guess, like touch sensitivity. You don't need to, it's not going to be quizzed upon. I thought it was just something interesting for you guys to know, so you don't really have to know it. Okay, so with that, we can now transition to circuits themselves. Actually, before that, give me a few minutes. I need a drink of water.
Oh, yeah.
Alright, let's continue. Okay, so finally we're going to get into actually looking at circuits. And this is, we'll call it section 2. So capacitors in series and parallel. The only rule that we need to invoke is this idea. That the change in voltage in any loop of a circuit is going to equal 0. So in any sort of a closed circuit, or any loop of a closed circuit, the change in voltage has to be equal to 0. And just to give you at least some sort of an explanation, remember the voltage was analogous to height in terms of gravity and the gravitational curvature. Who's rode a roller coaster before? Or who hasn't rode one? Ridden one? Rode one? Ridden one? Okay, likely everyone's ridden one before, right? Where you get off is also where you get off, right?
Yes. Where you get off is also where you get on. Or where you get off is where you get on.
Yeah, the second one. But why is that?
Is that a point?
Huh? No. But it's because the car or the entire roller coaster is in a closed loop. In a roller coaster sense, for it to be a closed loop, where you begin has to have the same height as where you end. Right? Because if they weren't at the same height, guess what's going to happen to the track or the car? It's just going to fall off, and then people are going to die, and that's going to be a serious problem. There is no loop unless unless the beginning height and the ending height are the same. Voltage is electronic equivalent of height. So for you to actually have a closed loop, the beginning voltage after you go across the full loop must have the same voltage at the very end. Okay? So this is all that this rule is stipulating. Here, we're going to talk about the different orientations of electronics. So electronics can be connected in series and parallel. So there's two different types of orientations. And this is actually going to be the topic of the lab tomorrow. So you don't need to bring your laptops tomorrow. let's first look at the parallel orientation. I'll first draw the schematic and then go over the description. Here we have our battery at the bottom, and our circuit is going to be branched at the top, let's say into 3 different paths. And on each path, there is a capacitor. And then these paths converge again. And let's call these capacitor C1, capacitor C2, as well as capacitor C3. Here we say C1, C2, and C3 are parallel because the same voltage is across each capacitor. And how do I know that? Well, it comes back to this rule. When you're going in a loop, every time you run across, so you just want to follow a single path. So let's designate a path here. So do you guys see the path that I'm discussing? Whenever you go across a battery, as long as it's in the correct direction, so from negative to positive, whatever voltage this is, you go up in that voltage. So let's say our loop began here. You would go positive V, and then you come across this electronic component, and then you would have to go down some voltage, let's say we'll call that V3, and then we have to close the loop. So in this loop, we have positive V minus V3, and this rule tells us that it must be equal to 0. Meaning, what is V3? It is whatever the battery was. So this tells us V3 is equal to V. We can come up with an alternate loop that only has C2. And what would you conclude the voltage across capacitor 2 to be? By the same argumentation, you'll get that it is the same voltage as the battery V. Same with V1. So here, V1 is equal to V2, which is equal to V3, which is equal to V. And that is one of the results of it being in parallel. You can also think of it as, just in terms of along this path, you can access C1, C2, and C3 all at the same time. You follow, let's say, the electrons, and then the electrons split, and then they'll hit all of them at the same time. And so these would be said to be running in parallel. If they are parallel, they have the same voltage as shown here. But we can be even more precise than simply specifying the voltage. And let's apply the capacitor equation to all of them. Q1, Q2, and Q3. Q1 is equal to C1 times V, C2 times V, which is equal to C3 times V. They have the same voltages, so we just called it the generic V over, as shown over there. Now, one of the things that is of interest to us is the total charge that is being transferred through our battery. What all of these, or there's going to be 3 positives and 3 negatives. The battery is taking charge from one and then giving it to the other. So this total charge is of relevance to us. And that would be simply Q1 plus Q2 plus Q3. But we have, instead of Q1, Q2, and Q3, we have from our capacity equation alternate ways to specify Q1, and that would be through C1 times V. Likewise for Q2, it will be C2 times V, as well as for Q3, it will be C3 times V. And here, what can be simplified, or how can we simplify this expression?
Take out the V's.
Yeah, factor out the V's, so you would get C1 plus C2 plus C3 times V. That is what the total Q is equal to. Now this expression looks very similar to our capacity equation, because our capacity equation tells us charge is equal to capacitance times voltage. Here, charge is equal to capacitance times voltage. So we can say this is equal to some equivalent capacitance, or the capacitance of an equivalent capacitor, where you get Q total is equal to CEQ times V. What this means is we can replace C1, C2, and C3 with CEQ to get circuit with identical behavior. So this 3 capacitor circuit we can simply replace with this one, and it will behave identically in terms of the capacitance, as long as the capacitance is equal to that. And in general, CEQ, when you have the parallel orientation, is the sum of the individual capacitances. Sum of the individual capacitances. And here, CEQ parallel is greater than all CIs. So when you have parallel, when you run capacitors in parallel, you are increasing the capacitance value. When you run it parallel, you are increasing the capacitance value. On series, on the other hand, you're going to be doing the opposite. So let's do series. As with parallel, I'm going to draw you the schematic before we go into the description. So in series, the top branch doesn't split whatsoever. All of our capacitors are along a single path. And the reason why it is called series is because when you follow the path of electrons, you would be running into C1, C2, and C3 in a sequence, one after the other, meaning series. Here, C1, this would have positive charge, positive Q. But the electrons would be drawn from here, and then it would accumulate onto this side, so that would be negative Q. So this one's positive Q. What would this one be? Well, we know that parallel plate capacitors, these must have the same charge. So this one's going to be negative Q, this is positive Q, this is negative Q, so on and so forth. So when they're in series, what is the same? Charge is the same. So notice Q's are the same in series. Whereas in parallel, what was the same for each capacitor? It was the voltage. In parallel, it's voltage. In series, it's the charge. So here, Q1 is equal to Q2, which is equal to Q3, which is equal to Q. And another thing that we know, by invoking that rule that I mentioned, so let's start by here and going across this loop. We would hit this battery, so we would get a positive V. Minus the voltage across capacitor 1, minus the voltage across capacitor 2, minus voltage across capacitor 3, and then back to the loop, meaning V minus V1 minus V2 minus V3, this has to equal 0. Or alternatively said, V is equal to V1 plus V2 plus V3. Now for each capacitor, we can write our capacitor equation again. So Q1 is equal to C1, they all have the same Q, so Q is equal to C1 times V1, Q is equal to C2 times V2, or Q is equal to C3 times V3. What we want to do is find an alternate form to represent the voltages, so we would isolate V1, V2, and V3 on those equations. So you get V1 is equal to Q over C1, V2 is equal to Q over C2, V3 is equal to Q over C3. And then when we apply it to our voltage equation there, we will get Q over C1 plus Q over C2 plus Q over C3. Now how can we simplify this? Well, we can factor out a Q for sure, but it wouldn't be Q over C. You would have to factor out a Q, and you would be left with, already like this, 1 over C1 plus 1 over C2 plus 1 over C3 times Q. Now this looks like, I know it doesn't really look like, but in terms of units, this is our capacitor equation. Here we have voltage is charge over capacitance, voltage is charge, and in the denominator we have capacitance. So this we want to define as 1 over CEQ. At which point this equation will turn into V is equal to Q over CEQ. By that, what we did was we simplified this circuit in series and we replaced it with a single capacitor with the capacitance CEQ, to get the identical behavior. Now, in general, one over CEQ for series is equal to the sum of 1 over CI. Now, here's what a lot of you guys are going to do, thinking that you can just simply do it. You can't flip the numerator and the denominator. More specifically, CEQ series does not equal the sum of CI over 1. Okay? You can't simply flip the numerators and the denominator. If you want to write it in terms of CEQ series is equal to, I will do that for you. This is equal to 1 over the sum of 1 over CI. And which is a reason why I wrote it like this, because this is even more confusing than the first one. So please do not do this. I'll go over an example of what this looks like in just a moment. Well, actually, let's do it for this one. Here, 1 over CEQ is 1 over C1 plus 1 over C2 plus 1 over C3. Or, let's say I wanted to get CEQ is equal to, here, then CEQ would be equal to 1 over C1 plus 1 over C2 plus 1 over C3. Instead, I really would recommend just using it in the form that I circled originally in the first place. And let's just go over one example and then we will call it a day. Oh, here I did want to say CEQ series is less than your smallest capacitor. So you put things in series if you're trying to reduce the capacitance. You put things in parallel if you want to increase the capacitance. So let's do an example. So determine, we want to determine capacitance of a single capacitor that can replace C1, C2, and C3. And this is the circuit. Given C1 is equal to C2, which is equal to C3, which is equal to C. So we have the circuit here, and we just want to find the capacitance of a single capacitor that can replace all the other capacitors and still get the identical behavior. In solving these problems, and you might think, wait, this is not series or parallel, it is series and parallel. And that is correct. In solving these types of problems, we want to just break things down into which are in parallel and which are in series, and then utilize the relevant expressions to narrow it down. So, in terms of doing these types of problems, you do want to do parallels first, and then the series. However, you need to start from small to large, so there might be problems where you need to do parallel, series, and then parallel, and then series again, and so on and so forth. In this problem, I would first recognize these two are in parallel. So, what I would first do is reduce this down to this simpler circuit where this is C equivalent of capacitors 2 and 3, and this is still capacitor C1. So I reduced these in parallel down to here, and now what kind of scenario do we have? Yeah, we have two capacitors in series, at which point I know that I can do or apply the series expression to get the CEQ of capacitors 1, 2, and 3. So let's call this step A, and let's call this step B, okay? So in step A, we had two capacitors in parallel, and so CEQ parallel is equal to the sum of the CIs. Meaning CEQ 1, 2 is equal to C1 plus C2. But you're given here, all of the capacitors have the same capacitance, so we can replace these with C, meaning CEQ 1, 2 is simply 2C. Now we have the capacitance of this guy, so we can jump to step B when we're considering these two capacitors in series. So here, step B, we want to do the series expression, so 1 over CEQ series is equal to the sum of the 1 over CIs. In our problem, we have CEQ 1, 2, and 3. This is equal to the two that are in series, which will be 1 over CEQ 1, 2 plus, did I say 1, 2? This is 2, 3. This is 2, 3. Apologies. Yeah. So then CEQ 1, 2, 3 is equal to 1 over CEQ 2, 3 plus 1 over C1. Where CEQ 2, 3 we discussed was equal to 2C, so this is 1 over 2C, plus the capacitance of C1 is simply C. Alright, well, in these problems, I'm going to need you to simplify things for me. So here we see fractions. How do you, in case we forgot, how do we add fractions? You need what to add them? Same denominator. We can always multiply things by 1. So we're going to multiply this by 1, except we want to do it in the form of 2 over 2. So that's how we get the same denominator on both sides. Meaning this is going to be equal to 2 over 2C plus, 1 over 2C plus 2 over 2C. Meaning this is equal to 3 over 2C. However, that's what 1 over the CEQ 1, 2, 3 is equal to. So CEQ here, because we only have a single fraction on both sides, we can flip these without any issue. We are mathematically consistent, so then CEQ 1, 2, 3, that is equal to 2/3 C. And that is the final answer. And this is all I was able to get to in the first section, so we will call it here. My personal belief is the class gets very easy for a little bit, and we are in that easy stretch. Hopefully you guys agree. Hopefully my opinion and your opinions are not super far off. Yeah. Yes, that is correct. Yes, that is correct. Alright, well, I will see you guys tomorrow, where we will be doing this in the lab.